Hello everyone, and welcome to topic 7 of Competitive Programming 1. Today we're going to be talking about queues, deques, and priority queues. Now, before we start the lesson today, I want to mention that I'm going to be trying something a bit new today. I'm going to be live coding the solutions to the example problems in today's slides. I hope that this will help you get a better understanding of the concepts, as well as how you might implement it in the code. Now, onto the lesson. We're going to start off by talking about queues. Queues are data structures that are first in, first out. You insert elements at one end and remove them from the other. Generally, problems that you can solve with a queue can also be solved with two pointers/sliding window, which are covered in topic 4, so I'm not going to be going over this too much. However, I'm going to be going over one practice problem just so you can see how it's done. Example 1, CapsLock. You are sending a message to a friend with a special keyboard. The keyboard only accepts lowercase letters and stores them in a buffer. When the @ key is pressed, it toggles the caps lock key. All letters in the buffer have their case flipped, as well as all subsequent key presses. You can sort of think like turning the caps lock key on or off. If it's on, then everything is capitalized. If it's off, everything is lowercase. And when the $sign key is pressed, the entire buffer is flushed. This means that everything is printed out to the message, and the buffer is emptied. Given some key presses, output the resulting message. So an example here would be this set of key presses here, right? We start by typing in A, B, C, and then we press the $sign, which flushes the buffer, which means it prints A, B, C to the message. Then we type D, and then turn on the caps lock key, which turns everything to caps lock, E, F, and then flush the buffer. Since everything is capitalized, we just have capital D, capital E, capital F in the buffer. And finally, or sorry, not in the buffer, in the message. The buffer is cleared. And finally, we turn the caps lock key off, and then have the letter G flushed to the message, so we would just have this resulting string. So since we're doing everything in sequential order, we can use a queue, right? We don't actually have to do any case changes while the characters are stored in the buffer, only when the buffer is flushed. This is because if the caps lock key is on, we know what all the cases in, like everything in the buffer is going to be uppercase. Therefore, when we flush the buffer, we just turn everything to uppercase. And similarly, when the caps lock key is off, then we know that all the letters in the buffer are going to be lowercase and we don't do any changes to them. So we just store a value representing whether the caps lock key is toggled or not, and then we can do our flush operation based on that. Now, on to the live coding. As you can see here, I've just written some skeleton code, just the method definition, the main method, and the imports. So let's just get started with creating our buffer. So we want to use a queue of characters, and let's call it buffer. And since queue is a abstract class, we have to use a linked list to represent it. Okay, cool. And we are also going to create a string to hold our final message, and a Boolean value to hold whether the caps lock key is on or off. Now, of course, you could just use string builder here if you wanted more efficiency, but here it doesn't really matter. It's just I'm just going to be using a regular string. Now I need to iterate through the keystrokes, right? So for each keystroke, so for int I equals 0, I is less than keystrokes.length I plus plus. We're going to get the character at that index. Okay. Now we have two characters that have sort of quote unquote a special effect, right? So we have a caps lock sign, right? And if it's entered, then we toggle the caps lock. So caps equals not caps. So this means that if it's off, then now it'll be on. If it's on, it'll be off. Or if C is the $sign, which is flush the buffer, we're going to take all of the characters in the queue and remove them into message. So what we're going to do, oh, my bad, it's just be else if. So we can just do while the buffer isn't empty, I'm going to use buffer here. While the buffer is not empty, we want to add the character to the message. But the thing to note here is that we actually want to change it depending on if the caps lock key is on or off. So remember that characters are technically just numerical values. So let's just first cast this to a car because we're going to be modifying it as a number. And then remember that if it's capitalized, lowercase values have a higher value than uppercase values. So we're going to subtract if the caps lock is on. So if the caps lock is on, we're going to be subtracting the difference between lowercase a and uppercase a. So this should turn any lowercase letter into its uppercase form. And of course, if the caps lock is not on, we just immediately add it in. Like this. And that should be it. Oh, right. One more thing. If it's a regular letter, can't forget, if it's a regular letter, we want to add the letter to the buffer. And finally, all we have to do is to return the message. Okay, let's save this and let's run this and see what we get. So again, this would be our example from the slides, and this would be what is expected. And we see that we indeed do get lowercase a, b, c, uppercase d, e, f, lowercase g. The second data structure that we are going to be talking about today is a deque, which is short for a double-ended queue. And it's a data structure that can add and remove elements from either end. It's not restricted to either one, or just one. So unlike a queue, which can only add elements at one end and remove it from the other, we can add and remove elements from both ends. Deques are useful when operations are needed on both sides of a list, and for the purposes of this class, they're all going to be pretty simple simulation problems, and it should be fairly obvious when you see it. So for our first example, we would have Backspace. You are sending a message to a friend with a special keyboard. Again, the keyboard only accepts lowercase letters, but when the sharp button is pressed, the last letter is deleted from the message. And so it's sort of similar to our caps lock, except we only have a single special character. Given some key presses, output the resulting message. Okay. So we would probably want to use a queue like before so we can store previous characters and pull them out in the right order at the end, right? But we also need some way of deleting the elements at the end when the sharp sign is pressed. So we can use a deque to allow operations at both ends. So again, in this example, we would have A, B, C, right, in our buffer. And then when we press the sharp key, we would delete the last element, right? So there's no more C here. And you can see in our final message is A, B, no C. D, E, delete the previous two letters, so these are also removed, etc., etc., and you can see how this would go. Now let's see how we would code something like this. Alright, let's start off by creating our deque again. And of course, since deque is also an abstract data type, we have to use a linked list. Then we iterate through the keystrokes, sort of the same way as last time. and set some variable equal to the character at. Okay, cool. And we do this similar thing as before. So if the character equals the backspace, right, we're just going to buffer.remove last. And else, if it's a normal letter, then we just do buffer.add last, the character. So notice that we actually have to specify last or front because for a queue, maybe there's only one side where you can insert and one side where you can remove. But for a deque, you can remove and insert from both sides. Okay, now this, we just have our message at the end after we've done everything. And remove the entire buffer. Dump the entire buffer into the message. Now notice how we want to remove first this time instead of remove last because we want to keep everything in the right order. And finally at the end, we should just return the message. Cool. So, oh right, I forgot this. And other than that, that should be good. Let's run it and see what we get. And yes, ABGHJKLMO, which is exactly what we were expecting. Let's also go over a second example for Deques, interview wait. You are sitting on a row of chairs waiting for an interview. When choosing the next interviewee, the interviewer will always choose from either the very left side or the very right side of the row of chairs. Furthermore, the interviewer knows exactly how much time each interview will take, and being lazy will always choose the side with the lower interview time. And you can assume that all times are distinct, so we will never have two times equaling each other. You are denoted with a -1 interview time, which means that the interviewer will always pick you over the person on the opposite side. How much time will it take before the interviewer gets to you? So, in our example here, this would be our row of chairs, right? And you're sitting right here. For the first interview, the interviewer will pick, oh, is 4 shorter or 3 shorter? 3 is shorter, so they pick this one or remove it. Again, which then, after that's done, which one is shorter, 4 or 2? 2 is shorter, remove it. Which is shorter, 4 or 5, remove it, and finally they get to you, because they pick you over the 5. And the total time elapsed would just be the sum of the previous times, right? So 3 plus 2 plus 4 is equal to 9. So given this array, we would, expect to get 9 minutes before the interviewer gets to you. And of course, we could just use a deque to simulate this process. It should be pretty apparent. And let's code it and see what we did. All right, so let's start off by making our deque again. Of integers this time because we are only comparing integers, not characters. And it's technically not really a buffer anymore, so I'll just call it deque for deque. Okay, and initialize the deque by just adding everything in. Cool. So we're just adding all of them in. Then we have maybe our total time and set it to equal to 0. Now while, I don't know, the deque isn't empty, although it doesn't really matter, we have our int, the next person to be removed, let's just call that R. So we just check if our deques peak first. So we're going to use peak because we actually don't want to remove it yet. We just want to compare it. So if it's less than, so if the time here is, the first one is less than the time for the last one, we're going to set r is equal to deques remove first. Okay, and I'm using poll here because that's just another method that you could use. Else we can have r is equal to dec.poll last. So basically here, this is all it's saying is if the first time is lesser than the last time, then we just remove the first one and store it in r. Otherwise meaning the last time is less than the first time, then we just take the last one out. Now we check if you were the one who got picked. So if r equals -1, we don't update the time. We know its time is up, so we just return time, right? Because that's just the total time that has elapsed since then. Otherwise, we're just going to add r to the total time. And Java is like fussy and doesn't like it if you don't have a return statement at the bottom, so we'll just return time again. So that should just be it. If we run this, let's see what happens. And we get 9, which was expected. The final data structure that we're going to be talking about today is a priority queue. A priority queue is a special data structure which prioritizes the removal of certain elements. And it has two operations: an insertion, which puts the item into the priority queue, and a removal, which takes the item with the first priority out of the priority queue. And in Java and Python, the priority is from smallest to largest. So if you put a bunch of numbers into a priority queue and start removing them one by one, you get the smallest number out first. But in C++, the order is from largest to smallest. So a priority queue would remove largest elements first. Now, if you wanted to sort it in a different order, you'd usually need to write a comparator, a custom function which compares two elements so that the priority queue will know which element to, take out first. But writing a comparator is usually cumbersome and it's really not time efficient. So an easy way to sort a priority queue in the opposite direction is to just multiply all the priorities by -1. Because when all numbers are negative, the largest number becomes the smallest, and the smallest becomes the largest, and we're essentially sorting in the opposite order. Just keep this in mind when removing elements, as you have to multiply it by -1 again if you want the correct priority. And finally, building a priority queue usually takes O of n time, which means that this is faster than just sorting an array if you had one. This means that priority queues are generally more efficient than that. Let's see the first example of a priority queue in action: movie theater. A movie theater prices its seats based on how many empty seats there are per row. For example, if a row has 5 empty seats, the seats in the row are priced at $5. Accordingly, as the seats in a row fill up, the price for each seat goes down. So if a person starts occupying it, now there's only 4 empty seats, then all the seats in a row are now only worth $4. The movie theater knows how many empty seats each row has, as well as the number of people coming to watch the movie. If the seats are assigned optimally, what is the maximum revenue that the movie theater can earn? Well, if we think about it, we can just always assign each next person to the row with the highest price. That would give us our best revenue. So, for example, in this case, we might have 5 people, and there are 3 rows, one with 1, one with 2, one with 4 seats. So we would assign the first person to the to the row with 4 seats, which means that we get $4. And then the seats in that row now have $3 left. And then we assign the next person to the same row, 3 seats left, because that's still the row with the most cost. So we have an additional $3 of revenue. Then we assign the next one to the one with 2, then one with 2, and then finally one with 1. This allows us to get a maximum of $12 of revenue. So we can use a priority queue, of course, to simulate this process. We just take the highest number each time, subtract it by 1, and insert it back into the priority queue. If it's the last seat, then we just remove it from the priority queue altogether. And finally, since Java sorts its priority queue from lowest to highest, we take the negative of all prices so we get the most expensive row first. And keep this in mind as we code the solution to this problem. So, as usual, we're going to just start off by creating a priority queue of integers. And generally I call mine PQ just for priority queue. And since priority queue isn't an abstract class, we could just initialize it directly. Then for the seats in the rows, so for each row, we add the negative of it to the priority queue. Now remember that we add the negative of it because Java sorts from smallest to largest. However, we want to remove it from largest to smallest. Okay, again, we're just going to create a total to count how much revenue we've accumulated so far. Then we just for the number of viewers, I'll fix this real quick. We just take the next one out. Right, so what this does, this should give us the next, like the largest number, right? Oh, maybe it should take out the negative of it just so that we get the largest number out of the priority queue. Then we just add the next to the total, right? How much money we're making. And then if next is greater than 1, then we add it back to the add the smaller number back to the priority queue, right? So pq dot add the negative of next minus 1. So what this would do is so because, for example, if we had a row with 4 seats and then we sold one of those seats, all the seats in that row would now only have $3. So this just adds it back to the priority queue so that we can take it out again in the next iteration if necessary. And finally, we just return the total amount here. So again, if we go to our example here, press run, what do we get? 12. And finally, for our last example, we're going to look at merge k sorted lists. You are given k sorted linked lists, and you want to merge them into a single sorted linked list. And a custom linked list definition is provided with just very simple a value and a reference to the next node. Now think about how we might accomplish this with 2 lists. All we have to do is to compare the heads of the 2 linked lists and add the one that's smaller to the end of the merged list. This is what happens in, say, something like merge sort. However, we can extend this to multiple linked lists by just comparing them and extracting the one that's the smallest. We can use a priority queue to speed up this process. When one is removed, the new head is added. So when the smallest head is removed, we add the next element back into the priority queue, and then we repeat until all the linked lists are empty. Finally, since we are comparing a custom class, we have to write our own comparator. We don't have like the -1 trick that we do if we were just using with integers. Personally, I like to do it with lambda functions, because they're just very easy to write and understand. However, you can write your own comparator class if you wish to do so. Let's code it. Okay, so again, I've written some starter code, and this time we have our ListNode definition, just simply an integer value and a next ListNode reference. I've also included a constructor and a toString method just to make things easier for us. So of course, let's start off by creating the head of our merged list. And setting the current node to the head. So this is because we want to return eventually the head of this linked list, but at the same time, we also want to add it to the end, so this is why we keep this current pointer here. Next, let's add our make our priority queue. And in order to use a custom comparator, we also have to set a size. I'm just going to set the size is equal to lists.length. And our comparator. Cool. And I think I'm here. Okay. So again, this comparator is just going to sort everything in the right order. Finally, we're going to add everything to a priority queue. So take our input list and add everything. Cool. Then, while we don't have, there are still elements left inside the priority queue. While there are still elements left in the priority queue, we take out the smallest one. So again, pull removes it from the priority queue. Then we set the current, so we add it to the end of our merged list. Then advance the current pointer. And finally, if we haven't reached the end of this linked list yet, we're just going to add the next one. We're going to add the next one back into the priority queue so we can retake it out if necessary. And finally, we're just going to return the end of this. We're going to return the entire thing. And notice that we're doing head.next because our head pointer is actually just a dummy pointer just to hold the entire merged list. So let's save this and run it. And of course we get 1, 1, 2, 3, 4, 4, 5, 6. And these were the original ones, so you can see it's just 1, 1, 2, 3, 4, 4, 5, 6 in sorted order. And that will be the end of today's lesson on queues, deques, and priority queues. Priority queues especially are a very important data structure with a lot of applications, so the homework for this set will have a heavier focus on priority queues with 2 questions focusing on them and 1 focusing on a deque. You'll notice that we're going to have no questions using a regular queue. This is because they're really similar to sliding windows and we've already covered those before. The homework will be due June 20th. And all I can say is good luck, have fun.